Hi, I'm Noah Goodman from Stanford University, and today I'm going to be talking about automating experiments with neural information estimators, or why the time is right for automated experiments. So recently there's been a lot of press about failures of the scientific method, in particular failures of replicability in many sciences, but especially our own science of psychology. One of many reasons that people have identified for these failures is the traditional method of first designing the experiment and collecting data, and only then specifying and doing data analysis. So a lot of possible fixes have been proposed. Um, One of them that's particularly interesting is pre-registration, in which the data analysis model as well as the experiment design are specified before the data is collected and then the analysis is done. Now, many people think of this as a constraint or a restriction on doing science. I like to think of this as a new opportunity. And the reason is because if you're specifying your data analysis model and your design before you do the experiment, you can start to think about how that data analysis model actually informs the experiment design, opening up automated experiment design and adaptive experiments. Now, to explain this just a little bit more formally, take this generative model that shows the relationship between the design of the experiment D, the observed data Y, and the latent variables of interest theta. Now, data analysis is basically the process of taking particular observed data from a particular experiment design and looking at the posterior over theta, given that data. But we can also think about how different that posterior over theta is from the prior, how much information we've gained from doing the experiment. So this quantity, the information gain, can be formally specified as a KL divergence between your prior knowledge of the latent variables of interest and your posterior knowledge after doing the experiment. Of course, before you've done the experiment, you don't know what data you're going to get. And so instead, what we have to think about is the expected information gain of doing the experiment. Now, the expected information gain can just be specified as the expectation of the KL divergence with respect to the data that we're going to see, or we can rewrite that explicitly as this integral. Now, this integral, it's pretty complicated, and indeed, the expected information gain is in general very hard to compute. It's hard to compute by hand, and it's something that most people probably don't want to try to compute by hand. On the other hand, if we're formally specifying our data analysis model, for instance, using a probabilistic programming language or some other system for explicitly formalizing data analysis, then in principle, we could ask a system to automatically derive the expected information gain from our data analysis model. This is a line of thinking that I've been excited about for a couple of years, and I've explored it in several different papers. I want to especially call out the first author, Adam Foster, of the last paper, both because he's been an intellectual force helping me think about these questions, and because a bunch of these slides are adapted directly from his. So thanks, Adam. So our first attempt to automate the computation of expected information gain using a probabilistic programming language was something we did using the probabilistic programming language WebPeople. And in the WebPeople implementation, it was very straightforward, and it used explicit enumeration for computing expected information gain as well as the inference components. And it turned out that this was pretty good for model comparison as long as the models were small. So an example of that was we took the classic experiment by Medin and Schaefer, which was designed to distinguish the exemplar from the prototype models of human category learning. So this experiment had a very simple setup. There were 5 examples from category A and 4 examples from category B. And after seeing those examples, people were asked to classify both the training examples and further generalization examples. So the question we asked was, this experiment, which has been used for decades and repeated and used to evaluate models, was it actually a good experiment with respect to the original goal of distinguishing the exemplar from the prototype model? So what we did is we computed the expected information gain across all of the possible experiments with 9 stimuli in 2 categories. And what we discovered, what you're seeing on the left is the distribution of expected information gain across experiments, the red bar is showing you which bin the original Medin and Schaefer experiment falls into, and the little blue bar on the right side of that plot is showing you the optimal experiment. Now, as you can see, the Medin and Schaefer experiment was basically totally average with respect to expected information gain. It wasn't at all optimal. So then we went and we wanted to see whether this would actually play out in experiments. So we collected human data from the optimal experiment and the original Medin and Schaefer experiment. And what you're seeing on the plot on the right is the actual information gain from the data as a function of the number of participants in the experiment. And you can see that the optimal experiment achieves the maximum information gain very quickly. The Medin and Schaefer experiment eventually gets there, but takes many more participants in order to distinguish the two models. So we did this using a package for optimal experiment design in the web people language. And it's pretty convenient to use, but it has a lot of limitations. In particular, because it's estimating expected information gain by doing an explicit enumeration, it only works for small discrete models. It doesn't actually work for parameter estimation, the kind of thing that you usually want to do in data analysis. So if we look back at the integral that defines the expected information gain, we can see that several parts of it are things that we probably know or we can probably estimate by sampling. But at the very least, this marginal density, the probability of the data given the design in the denominator of the log, is something that we don't know, and it's going to be very hard to estimate. Now, there have been a bunch of approaches for estimating this quantity and in general expected information gain. None of them has worked incredibly well, although many of them work well in specific situations. What we decided to explore was a different approach based on very recent work in statistics and machine learning. Now, this work has focused on the mutual information, and it has noticed that mutual information can be reformulated into a functional optimization problem. And function optimization is something that the modern tools from deep learning does extremely well. So our idea was to use these techniques in order to reformulate expected information gain estimation that we need for optimal experiment design problems into a function optimization problem that we can use deep learning for. Okay, now this slide shows you what looks like a lot of math, but it's actually a very simple derivation in which we start with the expected information gain integral, rearrange the probabilities using Bayes' rule a little bit, and then critically introduce an additional distribution Q over the latent variable theta. And we introduce it in a way that initially cancels. It's in the top and the bottom. But because it's in the log, we can split this into two quantities. And then we can use the fact that the integral on the right is effectively a KL divergence, and so it's greater than 0. Now, if we drop something greater than 0, what we get is a lower bound. So this is a lower bound that we've been calling the Barber-Agakov bound because we originally found it in a paper by Barber and Agakov. And what it tells us is that the expected information gain of a particular experiment design is going to be bounded below by this quantity, which depends on the function Q. So if we define the function Q as a differentiable family of functions, for instance, deep neural nets, we can then optimize by gradient descent in order to maximize the bound and use that as a proxy for our expected information gain. Now, the Barber-Agakov bound is not the only possible bound. One other bound, the Donskar-Varadon bound, is represented here, and I'm not going to write down the derivation, but you see that it differs both in the specifics of the mathematical formulation and in that the function family that we need to optimize over now is not a distribution over theta, it's a real valued function of theta and y. There are several other possible bounds on expected information gain that we can derive in a similar way. And in general, exploring alternative bounds and seeing which one works best, I think is a very interesting open problem and direction. Okay, so let's illustrate this idea with the simplest possible experiment. It's an A/B test, so there are two possible conditions that we can put a participant in. We're assuming that the response from a participant is going to be just a continuous real number, and we want to know which condition should we assign each participant to. So this is going to be implemented not in WebPeople, the language I was showing you before, but in a more recent probabilistic programming language called Pyro. Pyro is really good for doing things like continuous optimization in the context of probabilistic models. So the A/B analysis, data analysis model is written here, and we don't have to worry about the details, but what we have to give is a design that simply specifies which condition each person is assigned to. We need to give a prior, which tells us essentially what answer we expect each person to give, depending on the condition. And then that's going to give us a way of sampling the data Y that we expect to see. So as a little warm up, imagine that our priors are skewed. The first condition, we have a much wider prior over what we expect to see than the second condition. So we can either assign a participant to the first condition or the second condition. Here we can analytically compute the posterior, which makes it a little bit easy to think about this. So the posterior for the first condition, we start out with a very large amount of uncertainty and reduce it to 0.99. In the second condition, we start out with much less uncertainty, 4, and we reduce it to 0.8. So the question is, the one on the right, the second condition, the final uncertainty is less. But which do you actually prefer? So if we actually compute information gain, what we discover is that there's a lot more information gain from the first condition, because even though the final uncertainty isn't as low, we've reduced uncertainty quite a bit more. Okay, so now let's do this in a slightly larger scale and do simulations with the different information gain estimators. So we're going to assume we have 10 participants, and we need to decide how many to assign to the first condition and how many assign to the second condition. Now, this is a nice place to explore because we actually know analytically the ground truth expected information gain. And what we see is if we vary the design from all the participants in the first condition to all the participants being in the second condition, we see a nice gentle curve in expected information gain. What we're showing here is the ground truth in blue, several previously proposed estimators in orange and green, and then the two variational estimators that I described previously in red and purple. And you can see that the red estimator, the Dansker-Varadin estimator, is kind of all over the place, whereas the Barber-Agakov estimator turns out to be very, very close to the true values in this case. Indeed, the absolute error for the Barber-Agakov estimator is quite low, and it's by far the lowest of the estimators that we have access to. It also turns out to be the fastest. It takes the least time of all of the estimation approaches that we evaluated. Okay, so this tells us that we can fairly quickly and accurately estimate the expected information gain. But if we have noisy estimates of expected information gain, how should we go about actually finding the best experiment, especially if the space of possible experiments is very big? Now, I'm not going to go into the details here, but this is a great application of what's called Bayesian optimization, which is a fairly standard technique from statistics for finding the optimum of a noisy real-valued function. So we used the Bayesian optimization that is built into the Pyro probabilistic programming language. And as you can see, as we gather more data points, our estimate of the expected information gain function very quickly zeroes in on finding the true optimum, the best reduction in entropy. Okay. So this is pretty cool, but I don't actually think it's the setting that we're going to get the most bang for our pre-registration and formal data analysis buck. I think that's actually an iterated experiment design. So far I've said, hey, imagine that you are designing your experiment before you see any data whatsoever. What's the right experiment? That's fine, but after you've seen some data, you can also naturally ask, given what I now know about the variables that I'm interested in, the theta, what's the next experiment I should do? Or another way of saying it is, what's the next question I should ask of the next participant? So this gives us a loop, the iterated experiment design loop, where we start with some prior, we compute expected information gain, choose the best design, get data for that design, then use the posterior that we have from the new data as our prior and do the whole thing over. When we did simulations like this in practice, what we found is that the optimal iterated experiment design gives us both somewhat lower posterior uncertainty at the end of the experiment and also much lower variance in that uncertainty than just using a random experiment design. So overall, the takeaway that I'd like to convey is that there's a new paradigm shift in experiments happening, driven partly by new knowledge we have about the possible flaws with experiment procedure. That paradigm leads us to put the data analysis model and the design of the experiment first, before the data and the analysis. That opens up this really interesting new space of possibilities where we can first use modern techniques from statistics, new information estimators based on deep learning, um, and second, formal analysis specification using probabilistic programming languages and related things, and get the ability to automatically derive efficient adaptive experiments uh, from only the data analysis model as an input. I'm pretty excited about this, although I think there's a lot of work to do to show that this can be done efficiently and that it can be useful for everyday working psychologists and social scientists. Thank you very much for listening.